Hi, physics class. We're going to do projectile motion and vectors in this lecture. Just like last time, I need you to go get a calculator and I need you to get your formula sheet. And just like last time, no earbuds, take those out. And just like last time, this is not a calculator. Don't get one of those, get a real calculator. All right, let's do this. We're doing projectile motion and vectors. We have to start with vectors because you need them to work with projectile motion. So let's start with a simple example of what a vector is. And vectors are used when you're working in 2 dimensions. So let's imagine you're going to the library and you walk this path over here and then you go up. And you want to know, well, as a bird flies, how far did you go? What's your total displacement? That would be the hypotenuse of that triangle. And we can use that and do some math. I know you might need to pause because I go kind of fast. If you need to pause, just pause to write this down. When we look at vectors, this time we're going this direction, right? We're walking start to finish. But we're going to walk 95 kilometers east and we're going to walk 55 kilometers north. What is our total displacement? We can use math to figure that out. We have a triangle. One thing you need to know are these are resultants, and this is the resultant, excuse me, the hypotenuse. And the legs of the triangle are going to be called the components. All right. So when we throw something up in the air, we can break it down into 2 components. We can break down the horizontal component, this component, and we can look at the vertical component, and we can take the resultant and it will give us the motion of our projectile. All right. A lot of the stuff we're going to be looking at is throwing stuff off a cliff. And maybe from the last lecture, you remembered my d = 1/2 at squared. That'll be super important for projectile motion. We're going to use that a lot. A lot of stuff's going to fall off my lab station, or we're going to knock it off something and time it. This is key because if we have the distance, we can find the time. And you say, what's A? A is acceleration for gravity. It's the same as G, 10 meters per second per second. So as you can look at this projectile, it is going to go faster down than it does out. It's going to accelerate down. Why? Gravity. We break projectile motion into 2 separate components. We take the horizontal and look at this. Imagine this ball just rolling straight, right? It's just going forward straight. That's the vertical component. That's the horizontal component. That's the horizontal component. We're just moving at a steady pace off to the right. The vertical component is when we drop it down, and you can see that it gets more and more spread out. It speeds up as it falls due to gravity. The combination of those 2, you can see here, the lines for the horizontal movement are actually these lines going up and down. They stay at the same pace. They same at the same spread out, right? We go this far in 1 second. We go the same distance in the next second. We go the same distance in the next second. However, if you look at it as it falls, the lines become more and more spread out because that is an exponential thing as it falls due to gravity. All right, let's look at this diagram that's showing you the velocity for both the horizontal and the vertical component. And I want to look quickly at the horizontal component and just notice it doesn't change at all. Look, this arrow, this horizontal arrow doesn't change the whole time. Are you following it? All right, it doesn't change. It keeps going the same. Remember, this is no air resistance. This is the imaginary world of your physics classroom. The vertical component actually reverses itself. It starts by pointing up, and then it reverses itself, and it points down. The whole time it is accelerating down. I want to point out at the very top up here, the velocity up and down is 0. All right, but the acceleration is still negative 10 meters per second per second. It's still about to turn around and fall down. The velocity is 0, not the acceleration up there. All right. This slide basically has every single thing you need to think about in one slide for projectile motion. So take it slow, get a glass of tea if you need. We're going to look at kicking a football at 50 meters per second above, over this way. All right, and we're going to do it at an angle 30 degrees above the horizon. And we are going to look at how to find the horizontal velocity, the velocity this way. And we're going to look at how to calculate the vertical velocity, how far up is it going, all right? And to do that, we're going to use your old friend, SOHCAHTOA. We love SOHCAHTOA. If you don't remember SOHCAHTOA, it just is a way of remembering that sine is opposite over hypotenuse. And cosine is the ca part is adjacent over hypotenuse, and the TOA is tangent is opposite over adjacent. So as we look at our triangle, if I want to find the vertical component, that would be opposite of my angle here. And if I wanted to find the horizontal component, that would be the adjacent one, the cosine. So give it a try right now, just try it. It might be totally wrong. That's okay. Hit pause, see if you can calculate the vertical and horizontal component. Okay, hopefully you hit pause, you came back. Before I give you the answers, I want you to look at this and just notice that these are all velocity. When you do vectors, it's very, very important that the vectors all have the same units. You could do a vector analysis of the distance, but you can't mix and match. So you couldn't have the distance, it goes this way, and the velocity for these. It all has to all be velocity or all be distance. You can't mix and match. And the other thing I wanted to point out is that your vectors, for it to work, have to be head to tail. So this one, the head is touching the tail of this one, which goes up. That is head to tail. And you have to put your vectors that way for them to work, all right? It won't work if you have head to head or tail to tail. You'll get your motion backwards, essentially, is what will happen. All right, so let's look and see how you did on your horizontal. Hopefully what you got was the cosine of 30 equals the VH, that is the adjacent side, over the hypotenuse, all right? So the cosine of 30, and this is why I really want you to have a calculator, is you need to practice cosine in the calculator you're gonna have on the exam. It doesn't do you any good to practice it on your cell phone, which I'm gonna not let you use. So please put it in here and see how you do. Hopefully what you got when you did cosine of 30 is the 0.866. Make sure you get that correct, all right? And that's your answer. Now for the vertical velocity, it's the same thing, but we're going to do sine because we are using the opposite over hypotenuse. We're looking for the opposite. And so for sine of 30, you should get 0.5, and hopefully that's the answer you get. All right, now let's pretend we shoot a cannonball this way, and simultaneously at the exact same time, we drop a cannonball this way. And the question is, which one should hit the ground first? Answer should be they hit the ground at the exact same time, because the vertical component of this is the same for both, and it doesn't matter that we've added horizontal motion to one. Okay, if we shoot a cannon with no gravity, this is what it would do. It'd go straight up, right? But gravity acts on it, and gravity always acts in an exponential form. So let's take a look at it. It's going to pull down in the first second at 1 second, it's going to pull it down 5 meters. By 2 seconds, it's pulling it down 20. And at 3 seconds, it'll pull it down 45. Why? Because the distance equals 1/2 AT squared. And so time is getting squared for that. That's why it has a bigger effect. All right, how do you shoot something if you want it to go as far as humanly possible? Your brother is standing somewhere really, really far away and you have a Nerf gun. What angle should you shoot it at to hit him? 45 degrees is the correct answer. You will go the farthest at 45 degrees. What I find interesting is for the other ones, they end up at the same place if they add to 90. Maybe I can just demonstrate this and not try to explain it. Let's look at 60. 60 ends up here, and so does 30. 60 plus 30 is 90, and they end up at the same place. Or 15 ends up here, and 75 ends up at the same spot. 15 plus 75 also equals 90. Just something interesting to note. All right. In physics class, we do not do air resistance. So the ideal path is what we calculate. What's interesting is if you watch baseball players, they never run to the right spot where the ball's going to fall and just stand there and wait for it to go into their glove. They're always kind of adjusting a little bit, and that is because air resistance changes the path of that ball over and over again, depending on the air resistance of the day, which literally depends on altitude and temperature and stuff like that. So they have to kind of guess where it's going to go, and then they move around and adjust. All right, let's do one big fat calculation and just see how we do. We are going to take a projectile and shoot it horizontally off of a block, a cliff of whatever, of 20 meters high. So D is 20 meters. And we're going to see what the range is, how far the range is. All right, we know this is going to be 20 meters. And the initial velocity is going to be 10. All right, so how do we do that? Well, our given is D is 20. Gravity, don't forget to add gravity. It's given, it's on Earth, so put it as one of your givens, and your initial velocity. What we are looking for is R, which is also dx, or D in the x-axis, or you could even put dh here. D horizontal is also fine. The equations we are going to use are the regular V equals D over T, right? And we just rewrote it for D. And we're going to use the very classic D equals 1/2 AT squared with A being G. One thing I want to point out that makes life super, super easy when solving these, and it's not really ever easy, but it makes it a lot easier, is there's one ball that falls and hits the ground at one time. So since there's only one ball hitting the ground at one time, guess which variable is the same in all these equations? Yeah, the time. It doesn't matter where you're looking at the horizontal or the vertical. Time is interchangeable. So what we can do is a little trick that I like to do is just find time first. Just calculate time. And if we have the height of something, we can find the time, right? Look at it. We have the height. We know gravity. Let's calculate time. Once we have time, we can plop it in here and we're done. So try it now before I go to the next slide. Just try it. Hit pause. See how you do. All right. Let's see how you did. Here are your plugged in, substituted in numbers. We had 20 meters. It's falling. This 10 here is not the vertical motion of 10 meters per second. It's the gravity, 10 meters per second squared, right? Totally just, they happen to both be 10. Let's find time. We solve for time. Time is 2 seconds. We now take time and go figure out the horizontal motion, which is V equals D over T, and we just plug in that time, and we get the distance, which is it went a whopping 10 meters. Wasn't that exciting? Yeah, that was it. So I hope that helped.